Hello, good morning, everyone. That's really been a wonderful conference so far, as usual in Warsaw here. So thanks a lot to Simon and Michal. Where the previous two speakers have been focusing on mostly on dipoles in lattices and molecules in lattices. Actually, today want to advocate for experiments with molecules in the continuum. And in particular, I want to talk about fermionic ultracold molecules and how you can study the BCS-to-BEC crossover also from a polaron perspective, which could be a nice new kind of experiment you can do, which might be in some cases more feasible than reaching the super cold ultracold mixtures. So this is work we did together with the group of Richard Schmidt at the University of Heidelberg, and in particular, Eugen Deiser was the PhD student doing most of the calculations here. So, of course, there's a large interest in unconventional superconductivity in our field, but for example, also in condensed matter physics, and a very recent hot topic also in the field of two-dimensional materials. So this is a paper published last month where they actually claim to have observed chiral superconductivity in a new kind of graphene. And here you can see, for example, what their data looks like. So these are kind of phase diagrams with even 3 different superconducting pockets here as a function of the electron density, some external field. And even though these are very nice and tunable, which is different than bulk materials where you would have to make a new material for every point in this phase diagram, still you see that this is a very complex diagram with a lot of stuff going on, and it's still very hard to understand from first principles really what is happening, right? And with our quantum gases, even with ultracold molecules, which are already much more complex than atoms, we really can offer a new perspective and try to, for example, help people distinguish interesting characteristics of like P-wave superconductors versus S-wave superconductors. So I think there are very nice parallels here also between the field of ultracold molecules in particular and also two-dimensional materials. So of course, the BCS-to-BEC crossover has been one of the main success stories in quantum simulation with ultracold atoms. And for the people who are not so familiar, this takes place in a system where you have 2 species of fermions, let's say 2 spin states of lithium or sodium is not sure, sorry. If you tune across the Feshbach resonance, on the negative scattering length side, when there's not yet a bound state in the model, actually the fermions can pair together into Cooper pairs, right? But then if you go across the Feshbach resonance, this 2-body bound state enters the problem, and you go from a state where you have Cooper pairs to a state where you have actual bound molecules. And these molecules will then be bosons which form a boson-Einstein condensate. And it turns out to be a smooth crossover from a BCS state to a BC state. And this has really been, for the first time, really observed in ultracold gases. And even in the paper I just mentioned, they actually also refer to this BCS-to-BEC crossover and how their work relates to this. So this has really also made impact in other fields. And also, for example, in neutron stars, this has become very important. So what is very interesting about the dipolar molecules is that you don't even need a mixture to get the BC to BCS crossover, because even identical fermionic molecules, due to the dipolar interactions, can form P-wave bound states. Actually, these are also the field link bound states, which have been observed in Munich already. And this means that you can have a P-wave BCS to BC crossover in a system like this. Which would be a very nice analog to the chiral superconductivity I was mentioning before. And recently, with the developments in microwave shielding, it has really become possible to get these very cold molecular samples with evaporative cooling, but also to actually tune the scattering length and the dipolar length, which is needed to actually tune across this phase diagram. So now we're really in a very good spot to start to explore this very cool, interesting physics. However, as Xingyu was saying, you need to reach super cold temperatures to actually observe the P-wave superfluidity, making these experiments still very challenging. So there are other things you can do which might also be interesting experimentally. And just the fact that we have the P-wave superfluidity already with the identical fermions doesn't mean that the mixtures are not interesting as well. For example, if you take a hyperfine mixture of the ultracold fermions, you can have maybe again a version of the S-wave BEC to BCS crossover, but I can tell you for sure that the dipolar interactions will also here have a very strong effect on what will be the phase diagram. For example, you could imagine that your BEC of dipolar molecules forms a supersolid, or maybe even supersolid of BCS state, or maybe there are lots of interesting things you can imagine. And if you have a mixture, you could even see maybe signatures of S-wave pairing as B-wave pairing simultaneously. I think there's lots of interesting stuff to do. And one way to look at these systems is to do polaron spectroscopy. So instead of having an equal density mixture, you can go to the density imbalance limit, where you just have a few impurities of one spin state immersed in the bath of the other spin state. And this also gives you a very nice experimental tool to probe these systems, because what you can do is, for example, you can start with a system of identical fermions, here indicated in blue, and then you can drive a transition where a few of the particles are transferred to a different internal state. And in this different internal state, you would then have strong interactions with the other fermions in the system, right? And these different internal states for molecules, you have even a choice. You can use the hyperfine state, vibrational state, rotational state. This depends on the shielding scheme you like to employ and the physics you like to see. And this is the kind of spectrum you could expect. So here, what you would measure is the number of molecules which should transfer to the different internal state as a function of the detuning of your frequency of your transition from the Baire transition. So what you get is some kind of clock shift, because this molecule interacts now with the molecules in the background gas, and therefore the frequency of this internal transition changes, and this is what you can measure. So here, for example, you can see how the experimental signal as a function of frequency changes as a function of scattering length, and you can very nicely see here an attractive and repulsive polaron, and as well that at the resonance you get all kinds of stuff going on. So another advantage is that theoretically, just describing a single impurity is much more feasible than describing a whole strongly correlated system throughout the whole gas, right? Because if we have a relatively weakly interacting gas and we now insert this impurity, all the strong correlations are located around this impurity, making it theoretically easier to describe, while still offering insights into what happens if you have this strong correlations everywhere. Even though I say this, even just the single impurity problem is already quite challenging for these dipolar systems. So what we do is we build up the complexity in our work. So first start with a simple system to get basic understanding, and then of course we hope to relax some of these assumptions later. So what we basically do is we basically take this picture here. So we assume that we have permanent dipoles, and that the dipole of the impurity is much larger than the dipoles in the bath. So we can for now ignore the dipole-dipole interactions in the bath and focus mostly on the interaction with the impurity. And then it's also easier if you have an infinitely heavy impurity, because then you also don't need to care about this motion. So I will come back at the end of the talk what happens if you relax some of these assumptions. But yeah, this is just a starting point for us to start to get some basic understanding. And of course, it would be interesting to also look at what happens if you relax these assumptions. So in this system, you just have a quadratic Hamiltonian where the fermions have some quadratic dispersion, and they have, in this case, some interaction with your impurity, which is a dipolar interaction. And what is very nice is in this system, you can actually very nicely relate the ground state energy to the scattering properties of the system. Indeed, the ground state energy of the system is just given by an integral over the phase shifts summed over partial waves of the scattering problem between the impurity and the fermions. So this means that this already shows directly how this polaron problem is a very nice translation, intermediate step from few to many body physics, because you can directly relate now this ground state energy to the phase shifts that the scattering people like to calculate. Okay. So this is the kind of spectrum you would get for this dipolar polaron. So here we have the frequency and we have the scattering length. So I fixed here the dipolar length to a fixed value. And you see at the edges, so for weak attraction, for small negative scattering length, you just get a small energy shift, which is due to the attractive interaction. So you get an attractive polaron, right? At small positive scattering length, you get a small repulsive shift. But here in the middle, interesting stuff is going on. And we see multiple lines here. And it turns out that for these kind of strong dipolar interactions, the S-wave bound state and P-wave bound state, they appear pretty close to each other. So this means that if you have an experiment like this, you can, in one spectrum, see signatures both of the S-wave and P-wave pairing. And in the ground state, you have both the S and P-wave bound state occupied. So in this case, what is actually interesting, you can also see back the symmetry of the scattering problem back in your spectrum. Because we have parity conservation, the even L's and the odd L's, even and odd partial waves, they don't couple in the scattering problem. And this means that also your polaron spectrum is the convolution of the spectrum for the even partial waves and the odd partial waves. And that you have this S-wave bound state and the P-wave bound state, and the final spectrum then gives you the convolution, where the ground state has both of these states being occupied. So you can also look as a function of dipolar length. So this spectrum was for very large dipolar length, so you have KFAD is 1.5. And if you have smaller dipolar length, then the S-wave and the P-wave bound state become slightly more separated in the spectrum. And here for KFAD is 0.5, you see that the P-wave bound state and the S-wave bound state are pretty far, but you can still see both of them in principle. Okay, let me skip this. So what happens if you go to finite mass impurities? In this case, so for an infinite mass impurity, you can basically see that every state in the Fermi sea just gets slightly shifted with a phase. That's why we had this theorem I showed you before. But for finite mass impurities, you typically employ a different picture where you kind of do something which chemists call configuration interaction, where you expand in particle hole excitations on top of the Fermi sea. And if you do it like this, you can see that you don't just get the S-wave bound state or the P-wave bound state, but you can even get the coherent superposition of an S-wave and a P-wave bound state, which you simultaneously couple to. And basically, this can be done because the hole which you create from the Fermi sea also can have a certain parity, and this can compensate for the parity of your bound state. So this means that maybe you don't just have S-wave or P-wave pairing, but you can even get the combination of both together. Another interesting thing is if you don't take permanent dipoles, but for example, rotationally excited molecules, you don't just have dipole-dipole interactions like SZ-SZ, but you also have kind of flip-flop interactions. And in this case, you have a very interesting competition between the motional exchange between the particles and the spin exchange between the particles. Right, so to conclude, I think this polaron spectroscopy can be a very interesting spectroscopic tool to probe this BEC to BCS crossover, which you can maybe do already before going to the full many-body experiments. You would like to have a good shielding scheme in place. Yeah, of course, you do want to have very large dipole length to see something interesting, but I think that is feasible, especially with very strongly dipolar molecules. And in these experiments, you can then see simultaneous signatures of both S-wave and P-wave pairing. So some other stuff I'm interested in. So Martin already talked to you about the observation of halo trimers. So now we don't have only Feshbach dimers, but also Feshbach trimers. If you do this in the BEC, you can actually have superpositions of these dimers and trimers. And what I also find very nice is to look at the sporon physics in two-dimensional semiconductors, where this is a very nice probe where they use excitons to actually use the sporon physics to characterize strongly correlated states. So if you're interested in making connections between the physics in ultracold gases and in 2D materials, I'm very happy to discuss about this. So with that, let me conclude, and thanks for your attention. I'm happy to take any questions.
Thank you very much, Arthur. Are there any questions? Anna Maria.
Very nice talk. So for the P and S wave bound states, so this how that depends on the electric field, or what your assumption of the electric field?
Yeah, so basically now what we take is a dipole potential with a fixed dipolar length. And what we tune is in theory, you can tune basically the short range depth of the potential. So this is the parameter which we vary. So in practice, I mean, in experiment, I mean, with the microwave shielding, you have now several different detunings and Rabi frequencies, so that you could think of having a trajectory where you keep the dipolar length fixed and you vary the scattering length. And this is what we kind of would have in mind for the spectra we show here. So that is, if you keep the dipolar length fixed and vary the scattering length, that's when you would see first the S-wave state appear and then the P-wave state between the impurity and the fermion.
But you have the additional knob of varying the electric field.
So in this case, you would vary the parameters of your microwave dressing, which you use for the shielding. But I mean, if you vary electric field, you would simultaneously vary the dipolar length and the scattering length, and then I guess you would draw a different curve through parameter space, which I cannot tell you directly now how it will look. Yeah.
So there was one more question over here. Maybe we can pass the microphone.
Shielded fermions by modulating the microwave field elliptic state.
Mm-hmm.
And if the modulation frequency is resonant to somehow the high-fan states splitting like 100 kilohertz, we can create a superposition of two high-fan states. But the time scale is tens of milliseconds because this somehow this Rabi frequency is low.
Mm-hmm.
Position is happening pretty weak.
Mm-hmm.
But I think your result is pretty interesting. Just comment. We have created a mixture of high-fan states.
That's very cool.
And the shielding still work, but worse than single component fermions.
Mm-hmm. Yeah, I mean, then you will also have S-wave scattering instead of only P-wave scattering, right? So even, I guess this could increase your losses a little bit.
The critical temperature should increase to 20% Fermi temperature if you have two component dipolar fermions.
Yeah.
But unfortunately, the shielding is also worse. As I remember, at least 3 times worse.
So what is actually nice about this protocol is that in principle you start with your identical fermions, right? And then this is what you have for most of your duration of your experiment. And then you just do one pulse, which can be a hyperfine modulation of the microwave parameters, or you can do a two-photon kind of transition or something. And then you transfer a few impurities to this new state. And then immediately in the transferred fraction, you immediately project onto the eigenstates of this new kind of interacting problem. So this final state, actually, you barely need to have it for a very long time in experiment, which means that even if this is not very long-lived, that's not even directly a problem.
If we can find a really fast pulse to create a one impurity.
That will be a requirement. Yeah.
I saw that there was one more question, but maybe we postpone the discussion for the lunch break. So let's thank Arthur again.
Thank you very much.